Well, hey, good morning, team. Chemistry coach coming at you again. We are going to dig a little bit into physics today. I'm not going to get into the gnarly aspects of it. If you want to if you want to open the big door or go jump down that rabbit hole, take a physics class, especially if you can do X-ray diffraction in the physics lab. Typically, you're not going to do X-ray diffraction in an undergraduate chemistry laboratory. I remember we did it when I was getting my PhD. One of the people I was working with would head over to the physics department and take a crystal and go do an X-ray diffraction pattern. He'd always talk about von Laue. I got a Laue pattern, and I'm like, who's Laue? I was I was ignorant at the time. I didn't know. But we need to understand the basics of X-ray diffraction. Well, I guess, it's like a car. You don't need to know how the engine works to drive a car, right? So we realistically don't need to know how X-ray diffraction works in order to get the information from it that we need to accomplish our purpose as a chemist. Well, what's that purpose? Let's take a look. All right. Remember, our goal is what is the atomic radius? That's what we're after. We want to experimentally measure the atomic radius. Why do we want to do that? Because we need the atomic radius to be able to figure out the edge length of a unit cell, like FCC, BCC, simple cubic, and we went through how to relate the edge length L of the unit cell with the atomic radius. And it's different for each one, right? Based on the body diagonal, face diagonals, those kinds of things. So we already have done that. I'm not going to redo that. Why do we need the unit cell edge length? Because for cubic unit cells, that's the volume if you cube it, right? Volume is the edge length cubed. So now why do we want the volume? To calculate the density. So our ultimate goal for this entire trip, what a trip it is through solids, is to be able to take experimental data like the atomic radius and a known type of cubic unit cell, FCC, BCC, simple cubic, and be able to calculate, and estimate theoretically its density and compare that to an experimental value. Yay! Now, I could just give you R. I can just say, hey, bleh, here it is. But I want to give you a little brief introduction into how the X-ray diffraction technique works and a little bit of the theory behind it, because it's kind of cool. Nobel Prizes for everybody. Nobel Prizes for everybody. Let's look at the characters involved. Some pretty big giants in the physics community, and how and why they got their Nobel Prizes. Let's go through the basics of how we're after the atomic radius by hitting a crystal with X-rays. It's amazing they could do this. All right, none of this would have ever happened without the grandpapa of X-ray diffraction. I'm not going to get into the discovery of X-rays and all that fun stuff. We talked about that in first semester of general chemistry when we introduced electromagnetic radiation and all that fun sort of stuff. And way back we were looking at subatomic particles, right? So go back and review those videos if you need to. But what Max von Laue did back in 1912, right? It's amazing. Over 100 years ago, he was able to discover that crystals, right? Crystalline solids with regularly spaced atoms, so you can think of, atom. So you could have this distance between the atoms, right? This interatomic distance, we'll call that D for distance. He found that X-rays with wavelengths, because X-rays have pretty small wavelengths, they're super high energy. Thus, when you go to the dentist or doctor to get X-rays, you wear that lead vest, right, to minimize your exposure. And what was neat about X-rays is certain types of X-rays would have wavelengths approximately the same length as the interatomic distance. And when that happened, because of the orderly spacing of the atoms, the crystals acted like diffraction gratings. And the X-rays, so here's the surface of a crystal. So this cup holder one of my kids made. Happy birthday, Dad. That's what I put my tea on. Probably can't read this, light scattering off it. But if this is the surface of a crystal and you come at it with an X-ray of about the same wavelength as the interatomic spacing, it would undergo diffraction. So that acted as a diffraction grating. And from that, you could actually figure out information about the crystal structure, bond lengths, distances between nuclei, electron densities, those kinds of things. Kind of neat. So in 1912, he discovered that. Didn't really explain it theoretically. That takes the next couple of players. But that was a huge, huge discovery because it opened up that whole field of X-ray diffraction, figuring out crystal structures. So, of course, Nobel Prize pretty quick. I mean, that was a huge discovery. So we got the Nobel Prize in 1914. But the next two players, a father and son tag team, were able to put the theory to this, connect the experiment to the theory. But it would never happen, never would have started without Max von Laue. Yay! You ready for the next major player? So if you think of Max von Laue as the experimental part of it, you can think of the Braggs as the theoretical part of it, all right? The explanation of it. And this is a father-son team. So William Henry, the father, and Lawrence, the son, put together the theoretical explanations of X-ray diffraction and how you got a diffraction pattern and how you could deconstruct that diffraction pattern to give you information on the crystal, right? You know, where the atomic centers are, et cetera, you know, interatomic distances, plane spacing, et cetera. So back in 1913, and we're gonna go through a little bit of the background behind this because it's kind of interesting. And we're going to derive the famous Bragg equation that these two put together. So Nobel Prizes, 1915. Like I said, Nobel Prizes for everybody very rapidly after he did it because everybody was using this stuff to look at these crystals and go, ooh, fascinating information. I think, you know, like I said, I haven't read, you know, biographies of these people, unfortunately, but I think a lot of the initial theoretical thought was by the son Lawrence. He was only, I think it was 25 or something when they got the Nobel Prizes. So that I would put him under a category as possibly one of the youngest, if not the youngest Nobel Prize winner ever. All right. I mean, de Broglie was pretty young as well. But it's just like in your 20s, getting a Nobel Prize in your 20s is nutsoid. It's pretty cool, right? Just respect, no jealousy or envy, just respect. I think the dad took a little more, I think the son might have got screwed a little bit there. I think the dad took a lot more credit. But anyway, I'm just pontificating at this point. So let's look at the theory behind it. What they looked at with X-ray diffraction and derived the Bragg equation real quick. All right, put your geometry and trigonometry hats on for this one. So this is what the Braggs were thinking. And like I said, I'm not sure if originally it was the son Lawrence that had this idea that, so let's take a look at this picture. So here's kind of what Max von Laue was looking at. You've got this crystal. So let's zoom in on just the top two surfaces of a crystal spacing. All right, so here's the atoms on the surface, a regular array, next layer, right? And then you got the center of that one, the nucleus of that one. So you've got this distance between these planes, right? And that distance, would you agree, is just the radius of that one and the radius of that one. So the distance between the nuclei, or the centers of these atoms, or these planes, these interatomic planes, would be 2 times the radius. And our goal is to figure out what R is. So if we can get D, the interatomic plane spacing, the distance between the atoms, we can get R just by dividing it by 2. We good? All right. So how does this relate to X-ray diffraction? Okay, this is what the Braggs were saying. If we have X-rays coming in, we'll look at the experiment on the next board. So we're shooting X-rays monochromatic, right? So of one wavelength. And that wavelength, the distance between the peaks, should be approximately equal to the spacing between those, right? So that's the key. And so these waves are coming in, and they don't go very deep. I mean, they'll go, more layers than this, but it's only the top layers that really matter in this situation. So say this wave hits the electron cloud of an atom on the top surface. Okay, well, that's the electron cloud's polarizable, right? So it's kind of caused that to shift and move. And it in itself then becomes a radiator of X-rays, right? And so it absorbs the X-rays and then shoots them out. So you're getting a diffraction of these X-rays. And then same with this wave who comes in down in the second layer. So it hits an atom here that then becomes a source of emitting X-rays, which shoots off this way. Now notice wave B, which travels down to the second level versus wave A. Wave A goes boom, boom. Wave B goes, oh, and it's got to travel that extra distance there and then that extra distance there. So you see, I'll outline this in red. So you see that little extra distance there and that little extra distance there. That is how much further, that plus that is how much further that wave B has to travel from wave A in order to allow these to be in phase and constructively interfere, because they're going to have all these little radiating like dipoles almost, and so a lot of this is, they're going to interfere, and most of it's going to be destructive interference. But there's a caveat that there's a specific angle, so theta, this angle of incidence, you can actually in the technique change the angle that these X-rays strike the surface, and there are particular angles of incidence that allow maximum constructive interference, which gives you the most intense diffracted X-rays, right? So there's a particular angle giving a max radiation intensity. And what we'll do is we'll pull a detector over here. And that's where you get the X-ray diffraction pattern. And we're going to get the ones of maximum intensity. So we can, it's pretty simple in the experiment, just change the angle, right? Pretty straightforward. And you can move it all around the crystal, get it from every which way. So in order to get the maximum intensity, these two waves must be integral multiples of their wavelength, right? Integral multiples of each other. So let's take a look. Our goal here is to figure out what these lines are. We want to get that spacing there. All right, let's take a look at this. You ready? So remember sine, cosine, all those kinds of things? Let's do this in green. So let's take the sine of theta. And this is what the Bragg's played around with, right? Now remember, you've got this angle, so this would be the opposite. This would be the adjacent. This would be the hypotenuse, is that right? So SOHCAHTOE, sine is opposite over hypotenuse, right? SOHCAHTOE, that's what I remember from geometry. So that would be the opposite over the hypotenuse, right? That over that, that's what that is. So can we multiply h on the other side? But isn't h, right, that hypotenuse of that triangle here, equal to d, the interatomic spacing? Right? And this would be true over here as well. So if we rearrange this, move d over, then this would be d sine theta. So that little chunk of the triangle there would just be d sine theta. So if I have two of them, can I add those together? Right? That extra distance wave B travels would be 2d sine theta. Right? That's the extra distance traveled. That wave B travels. Right? I'm not going to get into gory detail, but hopefully just enough to make you go, okay, I think I got a basic understanding of how this X-ray diffraction works. Obviously, we're deriving the Bragg equation here. Now, that only occurs when we have constructive interference giving max intensity, okay? So that has to equal some integral of the wavelengths of the X-rays coming in, right? So the wavelengths are, approximately equal to d here. And in order for constructive interference to happen, you have to have this this diffraction order of a 1 or a 2 or a 3. It has to be an integer there. So this is what we call Bragg's equation. And so given this, right, and again, you don't have to understand all of this to be able to apply the equation. If I give you the angle of incidence, theta, the wavelength of the X-rays, the diffraction order, you could calculate d, right? And once you have d, just divide that by 2 and you've got the atomic radius. Now, we probably won't have time to do this on exams. Maybe on a homework or in a lab or a worksheet or something like that, we can work through this. But on an experiment, we're not going to have a lot of time to do this. A little more physics than chemistry at this point. So I'll probably just give you the radius, say from X-ray diffraction data, this is the radius of these atoms, and then we can use that to get the edge length of the cubic unit cell, which gives us the volume, and ultimately in the next video, we're going to get the calculate or estimate the densities from that. Okay, so that's just a kind of brief overview, a little review of signs and all this kinds of stuff. And if you want to go back and watch videos on electromagnetic radiation and properties of that from first semester of general chemistry, we talk about diffraction and interference and all those kind of refraction, fun stuff. All right, so I'm out of board space there. Oh, I'd love to leave that up. I'd hate to erase this. But let's take a look at kind of a basic X-ray diffraction setup, right? Not a lot of details, but a basic setup. Here's a very rudimentary look at the components of X-ray diffraction. Nothing fancy, but there's, probably a little 2, 3, 4 minute videos. If you're really interested, you could pop through. I was watching a few, just Bing or something like that. I binged them, right? Or you could Google them or Bing them, whatever weird verb we use now in today's technological world. So I saw a real cool one where a guy was going through doing an actual X-ray diffraction experiment. It was kind of neat. So he had the little crystal in there. He mounted it in there. It had a covered X-ray, showed where the X-ray tube was, the X-ray source, and showed how you could rotate the crystal around. It was really neat how you could change the angle of incidence. But in effect, here's a few major parts. You need a source of X-rays, probably a cathode ray tube or something like that, with some filament, some particular element in there. It's going to give you X-rays of specific wavelengths, right? That's going to give off all this radiation. And then we can use, if we need to, use a monochromator. If that's polychromatic radiation, more than one wavelength, we can get it down to one. We've got to collimate the beam, right? Get all the wavelengths the same, collimate it so we can strike the source, right? Which is the crystal source, right? So we've got in some thin crystal that can be mounted on a rotatable, tray or something. The one I saw, they rotated the what did they do? They rotated around the crystal, the detector. They rotated the detector. So this detector, they could rotate it around all the way around the crystal if they wanted to, and had a nice shielding so you didn't get blasted by your own X-rays and whatnot. And they had a way to monitor the voltage of the source here of the X-rays, and they had a counter to measure the intensity of the radiation coming off. So when those X-rays hit that, right, the electron cloud, the polarizable electron cloud, shifts, emits radiation in all directions, and you get and if the angle of incidence, remember the angle of incidence has to be such to give maximum intensity for constructive interference, and then you get this pattern where they strike like a photographic plate or a detector of one kind. And then you can take, I think that's what my friend was calling a Lowy pattern or something like that way back in the day. And from that diffraction pattern, once you get all around different areas of the crystal, you can actually get that interatomic spacing D using Bragg's equation and whatnot. From that, we can get the atomic radius. So again, I didn't go into great detail on it. If this is something, if you're more into physics and whatnot, and this really interests you, hey, dig into it. I just gave you a brief little glimpse into it. And again, all we really need is the radius of those atoms for what we want to do as chemists. All right, so little introduction into X-ray diffraction. Yep.